Knowing why we plot graphs and what graphs to plot is an essential part of A-level practical work in physics and in any science. There's a couple of obvious reasons why we plot graphs. We can show trends, line of best fits can show up anomalies, but more important, we can use the line of best fits to calculate different values. So let's take this example here. I've got stretching a spring, we've got a force extension graph, and we can eliminate the anomalies when drawing our line of best fit and use our gradient to work out our spring constant, force over extension. Line of best fit is effectively like a range of values. Rather than just taking one value, it allows us to find an average. The relationships between different variables changes slightly at A-level, gets a bit more complex. Let's take pressure and volume, which are inversely proportional. So the graph should look a bit like this, a curve going down. Now, to be able to prove they're inversely proportional, what we would do is replot our axes with 1 over v, or the inverse of v on the x-axis, which we should find they're a straight line because p is proportional to 1 over v. And that would prove that we've got an inversely proportional relationship rather than just trying to guess with a couple of points. So the idea is you can replot it to give something that's in direct proportionality. Let's look at another example. This is one from year 13. We've got force and how it relates to distance between two objects with Newton's law of gravitation. You'd get a graph that looks like this because the relationship between force and distance is an inverse square law, meaning that force is proportional to 1 over r squared. So if we replot the x-axis to be 1 over r squared, we should find again it shows direct proportionality. One skill that comes up time and time again in A-level practical papers is being able to make use of y equals mx plus c and apply it to a bunch of different equations and work things out from graphs once you've redrawn them. Now, just a quick recap, y equals mx plus c, y is the y-axis, x is the x-axis, m stands for gradient, and this plus c is the y-intercept. So let's apply this to our Suvat equation. Now, the Suvat equation we're going to use is s equals ut plus at squared, and the question might say something like plot a graph to find acceleration for an object being dropped using the gradient. So if it's being dropped, we can make a quick assumption to make our lives easier, which is u equals 0. So now we've got s equals half at squared. Now the graph we might plot might be how varying distances affects the time. So varying s affects t. But in our equation, the relationship is s is proportional to t squared. So we're going to have to replot our graph with this time s on the y-axis and t squared on the x-axis. Now once I do that, the middle bit, the half a, would therefore represent our gradient. So m is going to equal half a. So there should be a straight line because it's a directly proportional relationship. And to find acceleration, we would use the fact that gradient equals half a, therefore a equals 2 times the gradient, which in a free-fall practical should equal 9.81. Next practical to have a look at is one to do with EMF, so it'll be in the electricity part of your course. Now the general equation is the epsilon symbol, EMF equals VPD plus I current times by little r, which is internal resistance. And a question might say, find what the internal resistance is with a circuit that looks like this. So varying the current and measuring the potential difference across the battery. Now for this equation, I plotted the y and x axes first, and you need to rearrange so that V is the subject because that's what's on the y-axis. So to be able to do that, V becomes minus Ri plus our EMF. So my I is the x-axis. So let's have a look then. The thing that comes before it is minus R. So therefore my gradient must be minus R. And that then leaves this term at the end, my EMF, which is plus C. As you might be able to tell, because it's a negative gradient, it means it must be sloping downwards, which then makes sense that the y-intercept is equal to the EMF, or essentially the maximum energy per unit charge supplied to the circuit. Now, last thing, you need to be able to do this really complex equations, okay, including logs in year 13. So keep tuned. I'll do a video on those in the future so that you can make sure you can do it for any equation possible.